5.3, worst case efficiency of Quicksort. All right, so now we do the analysis. First, we do worst case analysis. It is relatively easier. All right, when we look at the worst case, based on our experience, we can guess for what situation we will get the worst case. So the worst case happens when the partition is extremely unbalanced. Based on the balancing principle, the best case should correspond to the most balanced partition. The two subarrays almost have the same size. In that situation, the overall performance is the best. So the opposite, the worst case. So the two subarrays, the size difference is the largest. So for, based on that understanding, so you will see one of the two subarrays is empty. So the most extreme case, all the elements are in one of the two subarrays. So one is this one, S region. So all the elements are in the S region. And we can call S case for simplicity. The other case, all the elements are in the L region. So we can call L case. Okay? So these two both correspond to the worst case. But if I ask you to compare these two cases, now, can you get some idea of which one is slightly worse, slightly better? Can you see a little difference between these two? Or we ask this question. We know they use n-1 comparisons. From the number of comparisons, they are equally good, right? The same. But other than the comparisons, can you see for some other things it is different for these two cases? Can you see that? So we may like to compare. So which one is worse or just equally bad? Here, I like you to look at the number of swaps. Not comparisons. Comparison, the same. But if you look at the number of swaps, can you see the difference? Right? For example, for the first one, S case, when you do comparison, okay, after you finish all n-1 comparisons, this P pivot element already in place, right? Its current location is the right location when the whole array is sorted. So this one is already in place. But for the L case, not in place, right? So after you finish n-1 comparisons, this P not in place. So you need another swap operation to make it in place. So that means the L case, you need to use one more swap operation than the one for the S case. So that's different. So that small difference, but it is different, right? So you can see slightly worse. The L case is slightly worse than the S case. All right. So after that, now we want to use mathematical analysis to see the worst case efficiency. Here we want to derive recurrence equation for the worst case. All right. First, we define a running time complexity function T of n and the problem size T. Time function T of n. Okay, yeah. Based on this extremal case partition, yeah, so we can derive the recurrence relation easily. Yeah. Because when we do the partition, we need to use n-1 comparisons. After that, we only reduce the problem size by 1. So when we call the recurrence function, so the size is only reduced by 1, n-1, T of n-1. So this is the recurrence equation. To solve this one, very easy. I think everyone can do that easily. Yeah. You know, summation from 1 to all the way through n-1. So you get this expression, 1/2 times n times n-1. Yeah. So this one we know it's big theta of n squared. Big theta of n squared. So not very good. We know it is pretty bad. Big theta of n squared. Yeah. Remember when we study selection sort, bubble sort, insertion sort, these three, the worst case, all in this category. Yeah. But when we study the merge sort, that is different. For merge sort, the worst case is big theta of n log n. Yeah. So this property makes the merge sort very special. And it could be useful in some special situation in the real world applications. Yeah. So here, I mentioned this another time. I remember I talked about that several times. Yeah. Next, I want to use one simple example to show you this worst case scenario. Yeah. All right. So let's look at this simple example. Yeah. The array is sorted in reverse order. Okay? Reverse order, decreasing order. Okay? Yeah. But we want to make it increasing order. We use the Quicksort to make it in increasing order. So we do partitioning step by step. Yeah. The first round, it is an L case because other than the pivot element, all the elements are in the L region. Yeah. So after we do the partitioning, we need to do one swap operation. After that, this one is in place. So I use a different color. Yeah. So this, red, orange type, color. Yeah. In place. Yeah. The remaining elements, then we do another partition. This time, 8 is the pivot element. So you can see it is a S case. Right? So other than the pivot element and the element in place, the remaining elements are all in S region. Yeah, so in place, S case. So after that, we don't need to do swap, right? Yeah. After comparisons, we don't do swap operation, and we get another element in place. Element 8 in place. Yeah. Remaining elements, we use 2 as the pivot, and it becomes an L case. Yeah. So then after that, we do one swap, put 2 in place. Remaining elements, 7 as the pivot. So it is a S case. Okay. Then no swap, 7 in place. Then next time, 3 is the pivot. So it is an L case. Right? So then one swap, we need to do one swap. Then the last 2 elements, 5 is the pivot, no swap, it is in place. the last element automatically in place. Yeah. So that's you can see this worst case special situation, this worst case, when we run the partitioning from beginning to end, you can see every time, every round, we have a worst case. Yeah. Sometimes L case, sometimes S case, alternatively, yeah, in that pattern. Yeah. All right. So, yeah. So this is the worst case video part I.3. Yeah. Next, in our last video, we will do analysis for best case efficiency. Yeah. All right.